All right, two more trig substitution problems for you in the last trig substitution video that we're going to have. Both of these are going to have a twist off of what we've done before, but I think they're going to be fun twists and we'll enjoy them. So first one, seems totally unrelated. Prove the area formula for a circle. So let's do this. Let's see here. Let's put a circle on our coordinate plane. Now, it said prove the area formula for a circle, which we know to be pi r squared. So the circle that we're putting on the coordinate plane needs to have a radius of r. It just has to work for any radius that we want. So this is going to be r, this is going to be negative r, this will be r up there, this will be negative r up there. So this is an area problem. Okay? Now, in calculus, when we here find an area, we're thinking a definite integral. So how are we going to do that? Well, first off, what's the equation of this circle? I chose to put the center at the origin to make this as nice of an equation of a circle as we can. That would be x squared plus y squared equals r squared. Now, this is an implicit equation, and when we take integrals, we want them to be explicit. We want them solved for y. So if we solve for y, we have y squared equals r squared minus x squared. Take the square root of both sides, y equals plus or minus the square root of r squared minus x squared. Okay, so this is an area problem. We know a definite integral is going to find the area under the curve between that and the x-axis. So what we can do is we could just take the top half of the curve, we could get rid of that minus, and we could take the top half of the curve and find the area under that from negative r to r, and then how would we find the area of the entire circle? Well, we'd just double it, wouldn't we? Okay. Even more simply than that, even more simple than that, let's not go negative r to r. Let's just go, let's just go 0 to r. Let's just find this area right here. Okay. Because we know when we find definite integrals, we use our fundamental theorem of calculus. We're going to have to plug in our bounds. And I like plugging in 0 better than most things. And I think that's the nice and simple, nicest thing to substitute in. So our area is not going to equal the integral from 0 to r. It's going to equal 4 times the integral from 0 to r of the square root of r squared minus x squared dx. So that's the integral that will allow us to prove the area formula that it really is pi r squared. Now, in the past, I'm sure in geometry or at other times in classes, you've come up with the logic behind the area formula for a circle. You've maybe talked about cutting them up in slices and reorganizing them, stacking them to make them look like a parallelogram. Those type of things. Well, here is a true calculus proof of the area of the circle. Now, when you take a look at this, we have a square root. Okay, so that makes me start to have my alert turned on here to trig substitution, and I have something squared minus x squared. Okay. And it reminds me of 1 squared minus x squared. And 1 squared minus x squared, if I go back to our Pythagorean identities, could be something like 1 minus sine squared or 1 minus cosine squared. I'm going to choose to let my substitution be with the sine to eventually get to a cosine squared. Okay. Now, let's let x equal. Now, I don't want to just choose the sine of theta because that would give me r squared minus sine squared. And just like on our previous examples from our last video, when we had a 9 there, we wanted a 9 in front so we could factor that 9 out. Okay, same with the 4 in the problem before. We wanted a 4 in each to factor it out. So the substitution that we want to do is r times the sine of theta. That way when we squared it, there's going to be an r squared in both terms that we can factor it out. So this is going to equal 4 times the integral from 0 to r of the square root. There we go. R squared minus, are you guys okay with me just jumping to this step? R squared sine squared of theta? Okay, I mentioned that in the last video. You're going to start to be able to skip some steps here. Oh, I have to finish my substitution, don't I? What does dx equal? Well, what's the derivative of r times the sine of theta? Well, it would be r cosine of theta, so we'd have to multiply the d theta over. Dx equals r cosine of theta d theta. All right. 4. Definite integral from 0 to r. Take out your r squared. We have 1 minus sine squared. About like that. Now that 1 minus sine squared is going to become a cosine squared. Okay, let me just double check. R squared cosine squared, then an r cosine. Good. All right. Making progress. 0 to r. Square root of r squared cosine squared is just r cosine of theta. So we have an r cosine of theta times an r cosine of theta, which is r squared cosine squared of theta d theta. Okay. Now remember, our variable here is theta. It's not r. R is a constant term. It's the radius of the circle, and the radius of the circle is not changing. We're just picking it to be r. We could have picked it to be 1 or 4 or whatever. So let's factor out that r squared. And we have that. So we need to be able to find the antiderivative of cosine squared. We have done this before. We did this back in integration by parts. Let's see here. I have it written down handy. You might need to look it back up. You probably should have added this to your derivative antiderivative book at some point here. So we have 4r squared, antiderivative of cosine squared, okay, is 1/2 cosine of theta sine of theta plus 1/2 theta, and this is from 0 to r. Okay, so we found our antiderivative. We use what we've done in the past, which we like to be able to do. Now let's substitute in our r, substitute in our 0. So we have 1/2 cosine of r? What do you mean cosine of r? Oh, I totally forgot to do something. Okay. When we changed our variables, okay, and I warned you guys about this a lot way back, even before our last test, our variables here were for x equals 0 to r. But then we changed our variable to theta. So we need to change our bounds to theta bounds. Now let's think about it here. If x is 0, what is theta? If x is r, what is theta? Okay, so x equals 0 corresponds to theta equaling what? What is r times the sine of 0? Well, the sine of 0 is 0, so that's just 0. Okay. How about... Oh, I did that backwards here. My apologies. Okay. What does theta equal here? The arc sine of x over r. There we go. I put 0 in for theta, not in for x. My apologies. Okay, so we have x equals 0. What does that mean for theta? Well, the arc sine of 0 over r is the arc sine of 0. What angle has a sine of 0? It's still 0, but I wanted to fix that, so I apologize about that. All right, how about when x is r? What does theta equal? The arc sine of r over r, which would be the arc sine of 1. The angle whose sine is 1. What angle has a sine of 1? Where does that happen on our unit Oh, look there, there's a circle. Where's that up in our unit circle? At pi over 2. Are you shocked here that we're changing our bounds from x equals 0 to r to theta equals 0 to pi over 2? All right. Okay, taking me a moment here. Almost there. And I'll just pause the video and finish doing these. All right, so I changed all of those. So we are not taking 1/2 times the cosine of r. We're taking 1/2 times the cosine of pi over 2 times the sine of pi over 2 plus 1/2 times pi over 2 minus, now we're going to put in our 0, 1/2 cosine of 0, sine of 0, minus 1/2, I'm not fitting it on the page there, times 0. There we go, we're good. All right, 4r times, what do we have here? Let's see, well, the cosine of pi over 2, what's the cosine of pi over 2? Cosine of pi over 2 is 0, which means this whole term is 0. Okay. We have a pi over 4. I lost my squared on that r too, didn't I? All right. Minus, okay, well, we put in zeros here. What's the sine of 0? Sine of 0 is 0. So what does that do to this term? Gone. What's 1/2 of 0? That's gone. The only thing that's left in those brackets is pi over 4. And what happens when we take 4r squared times pi over 4? The 4's cancel, and we have pi r squared. So the area of the circle is pi r squared. Very good. Okay, running out of time. I have 3 minutes. I don't know if I'll do the whole example, but at least we'll set it up. Take a look at this one. Hey, what's different about this? Well, now we've got a pesky x there, don't we? Okay. If this was x squared plus 4, 9, 1, we'd like it. Even the 6 could throw us off here a little bit. That'd be a challenge, but we could still figure that out. We just have to put a square root of 6 in as part of our substitution. But it's that x that we're having a hard time with. We really like it when we have x squared plus something or minus something. We want something squared. We want it to look out nice. We don't want x's in there. So here's what we're going to do. We're going to complete the square. It'd be really nice if this was a plus 9. Because if that is a plus 9, this is x plus 3 squared. Okay. However, we can't just add 9. Okay. That changes things. If we add 9, we also have to subtract 9, so we're not really changing the value. So what I'm doing is adding 9 and subtracting 9. Okay. Now, this first part is still x plus 3 squared, but now it's minus 9. Do you see that we have something squared minus 9? And we should be able to handle this. Here's my substitution. Okay, something squared minus 1. Let me just go back to my identities, make sure I don't goof this up. Something squared minus 1. Okay, that reminds me of this. So I want that something that needs to be squared to be secant. So I am going to let x plus 3 be the secant of theta. All right, so what is dx? Well, dx d theta, if I take the derivative of 3 is just 0, so that's gone. The derivative of the secant is the secant times the tangent. Okay. Now, this would work out great, but we would have a secant squared minus 9. We don't want just secant squared minus 9. We want 9 secant squared minus 9. So I'm going to have to put a 3 there so that when we square it, that's what we get. So we have dx over x plus 3 squared. 9 secant squared of theta minus 9 times 3 secant of theta tangent of theta d theta. This is going to be a tangent squared. There's going to be a lot more to do, but our video is over now.